calculated, and that will be 0.24 ampere is the maximum current. Well, that was a very simple problem. Let's now look at LCR circuit. What does LCR stands for? We have an inductor, capacitor and a resistor all combined in one circuit, an LCR circuit. You know by now that in a pure resistor circuit, voltage and current are in phase. In a capacitor circuit, current leads the voltage by 90 degrees. In an inductor circuit, the voltage leads the current by 90 degrees. Well, what happens when all these three are connected? Here we have an alternating current source connected to a resistor R, an inductor L and a capacitor C. I have used some values, we can ignore them at this time. So a resistor of resistance R, a capacitor of capacitance C, an inductor of inductance L are in series and connected across a generator of EMF E. Well, of course, that is the RMS value. The current in the circuit is determined by the inductive reactance XL, the capacitive reactance XC, and the resistance R. So it's a combination of all these three that is going to determine the total current. Now, if F is the frequency of the AC, then you know that the inductive reactance is 2 pi FL, and the capacitive reactance is 1 over 2 pi FC, and the resistance is R. Now, if VL is the voltage across the inductor and VC the voltage across the capacitor, VR the resistance across the voltage across the resistor, not the resistance across the resistor, the voltage across the resistor, then you know that VL equal to I times XL. That is the equation for the inductor, is that right? The basic Ohm's law, V equal to IR. Replace R by the reactance. So VL is IXL, VC equal to IXC, and of course VR equal to IR. Those are the individual equations that gives you the voltages across each of these. The potential drop across the resistor and that across the reactance are at right angles to each other. Is that right? Yes. The potential drop across each of these are not in phase. The current in an AC circuit not only depends on the resistance value but also on the reactance. Since the reactances XL and XC are 100 degrees out of phase, you see, if XL is upward, then XC will be downward. Because in a capacitor, the current leads by 90 degrees. In an inductor, the voltage leads by 90 degrees. So there is a phase difference between XL and XC of 180 degrees. Therefore, the net reactance, when you have the two of them together, because if one is upward, the other is downward, the net reactance will be XL minus XC. Well, either XL minus XC or XC minus XL, it doesn't matter. So here, if this is XL, this is XC, and this is the resistance. So these are the three components in that circuit. The resistance is at right angles to both XL and XC. Now, the combined effect of resistance and inductance in a circuit is called the impedance. We talked about this, represented by Z. The total effect of all these reactance and resistance together we call impedance. And if this is the total impedance, it is due to the net reactance. Look at this, XL minus XC is this vector. R is this vector. Therefore, the total impedance is the third side, which is the Z. So Z squared equal to R squared plus XL minus XZ squared. So this is the total impedance for the LCR circuit. And what is the current in the circuit? The current is determined by the impedance. So that will be I equal to V over Z. Power P is E RMS times I RMS cos phi, where phi is the angle between the resistance and the impedance. And the tangent of that angle is XL minus XC divided by R. And cos phi equal to R divided by Z is called the power factor of the LCR circuit. Now that's one term that you need to remember. Cos phi, which is R divided by Z, is called the power factor of the LCR circuit. Now, what is a resonance circuit? Very often this is used in electrical engineering. In a circuit, if the inductance and the capacitance values are such that XL equal to XZ. Now remember, XL and XC are 180 degrees out of phase. That means if the magnitudes of these are the same, then XL minus XC will be equal to 0. Now such a circuit will be now controlled only by the resistance. So the total impedance then will be equal to the resistance only. The current then will be a maximum because the reactance, the net reactance is 0. The maximum current then will be I equal to V over R. And such a circuit is said to be a resonance circuit. When the circuit is adjusted for resonance, the net reactance is 0. The maximum current, the current will be a maximum at that time. And we have a resonance circuit. In fact, when you tune a radio or television, you're actually tuning using the condition of a resonant circuit. So the condition for resonance is XL equal to XZ. XL is 2 pi FL. XC is 1 over 2 pi FC. So if F0 is the resonant frequency, then 2 pi F0L will be equal to 1 over 2 pi F0C. Now, when this happens, we call the frequency to be the resonant frequency and be represented by F0. Can you use this to solve for the resonant frequency? It's very simple. Cross multiply and solve for F0. F0 will be 1 over 2 pi square root L times C. You will see this a lot in electrical engineering. Let's do an example. Find the impedance and the current in the circuit shown on the right. All the values we have E equal to 110 volts, that's the RMS value. The frequency of the AC is 50 Hertz. The resistor has a value 4 ohms. The inductance is 27 millihenry. And the capacitance of the capacitor is 380 microfarad. Well, we got the frequency, inductance, capacitance. First we find XL and XC. Simply use the formula. XL is 2 pi FL, and that will be 8.48 ohm. And how about XC? XC is 1 over 2 pi FC. Use all the given values. That will give you 8.38 ohm. Well, if you see here, it's almost a resonance circuit because the two reactances are almost equal. In other words, because they are 180 degrees out of phase, the net reactance is XL minus XC is 0.1 ohm. It's a very small quantity. So what's the impedance? The impedance is square root of R squared plus XL minus XC squared. So that will be, I'm going to use that XL minus XC, the net reactance. So Z equal to square root of R squared plus X squared, and that's equal to 4.0010 ohm. You got the total impedance, and that can be used now to find the total current. I equal to V RMS divided by Z. V RMS is given to us 110 volts. Therefore, I RMS is 27.5 ampere. Now, F0 is 1 over 2 pi square root LC. F0 is the resonant frequency, and that will be, using the values of L and C, it will be 49.7 Hertz. The one we have used is 50 Hertz. So if the frequency now change slightly, that will be the resonant frequency of that circuit. At that frequency, the capacitive reactance will be equal to the inductive reactance. They will cancel each other, and the circuit will be purely a resistive circuit. Alright, another example. A series LCR circuit with L equal to 2 Henry, C equal to 2 microfarad, and R equal to 20 ohm is driven by a generator with a maximum EMF of 100 volts and a variable frequency. Find the resonant frequency F0, the power factor for the circuit when F equal to 64 Hertz. Well, first, resonant frequency. F0 is 1 over 2 pi square root LC. We know all those values. The resonant frequency is 80 Hertz. The inductive reactance is 2 pi FL, and using the values we have 804 ohm. And the capacitive reactance by using the given values is 1239 ohm. So what is the net reactance? Net reactance is XL minus XC, that is negative 430 ohm. What's the total impedance? Total impedance is square root R squared plus X squared, where X is the net reactance, and that will be, we have now calculated X. You can see that negative value will disappear when it is squared. So the net impedance is 430.5 ohm. We need to find the power factor. The power factor is cos phi. If you remember that diagram we had, cos phi is R divided by Z. So we got R and we got Z. Therefore, cos phi equal to R over Z. That will be 0.046.